This research paper introduces an improved physics-informed neural network, I-PINN, that mitigates gradient-related failures by enhancing the uncertainty weighting method from previous work. The proposed IAW-PINN sets an upper bound on adaptive weights, preventing excessive suppression of residual term weights and avoiding ill-conditioned optimization problems. This ensures convergence and adherence to constraints, improving both boundary condition and residual term accuracy. The I-PINN method effectively addresses the issues of substantial fluctuations in solution outcomes observed in IAW-PINN, significantly enhancing robustness across diverse network structures and improving the model's generalization capabilities. The authors demonstrate that I-PINN significantly enhances solution accuracy, achieving improvements of at least an order of magnitude over PINN, IAW-PINN, and IA-PINN. The network structure is composed of feed-forward neural networks, where the number of hidden layers and neurons per layer are varied to test the robustness of the I-PINN method. The relative error is evaluated for different network structures, showcasing the improved performance of I-PINN. The graphical abstract illustrates the minimization of the ATOM and LBFGS optimization algorithms, highlighting the improved feed-forward networks and adaptive weighting in the I-PINN approach. The author's contributions can be summarized as follows. First, they enhance the uncertainty weighting method to prevent excessive suppression of residual term weights. Second, they develop I-PINN, which effectively addresses the issues of substantial fluctuations in solution outcomes. And third, they demonstrate the significant improvement in solution accuracy achieved by I-PINN. The proposed method has the potential to improve the stability and accuracy of physics-informed neural networks, making them more reliable for real-world applications. Physics-informed neural networks, PINNs, have revolutionized scientific computing by integrating fundamental physical principles with advanced data-driven techniques. However, PINNs face challenges with stiffness and gradient flow, limiting their predictive capabilities. To address this, an improved PINN, I-PINN, is proposed, combining the strengths of neural networks with an improved architecture and adaptive weights containing upper bounds. I-PINN achieves enhanced accuracy and accelerated convergence without introducing extra computational complexity. PINNs extend beyond conventional deep learning frameworks by incorporating fundamental physical principles, enabling them to effectively address complex challenges across various disciplines. However, their effectiveness relies on achieving a delicate balance among multiple loss terms, each representing a distinct facet of the physical constraints imposed by partial differential equations, PDEs. To address this challenge, various adaptive modifications to the vanilla PINN framework have been devised, categorized into four principal categories: refinement of the loss function, enhancement of the network's representational capacity, adaptive configuration techniques, and domain decomposition methods. These advancements aim to enhance the optimization process, convergence properties, and representational capacity of PINNs. For instance, adaptive training weights ensure a balanced emphasis across the training process, while min-max architectures balance error minimization with robustness enhancement. Sophisticated network architectures and adaptive activation functions enable the network to capture intricate data patterns. Adaptive configuration techniques dynamically adjust the network's parameters to better suit the problem at hand. Domain decomposition methods segment the problem space to address multi-scaled challenges more effectively. The proposed I-PINN combines these advancements to mitigate gradient-related failures. Numerical experiments with various benchmarks illustrate the improved accuracy and generalization of I-PINN. The supporting data and code are accessible, enabling broader research engagement. By employing robust optimization algorithms and meticulously tuning their parameters, I-PINN demonstrates the capability to enhance accuracy by at least one order of magnitude and accelerate convergence without introducing extra computational complexity. The physics-informed neural network (PINN) framework has been widely adopted for solving partial differential equations (PDEs), due to its ability to incorporate physical laws into the neural network architecture. However, existing PINN methods often suffer from gradient-related failures, leading to inaccurate predictions. To address this challenge, this paper proposes an improved PINN, I-PINN, that integrates the strengths of two existing methods: the improved architecture for PINN, I-PINN, and the improved adaptive weighting method for PINN, I-PINN. The I-PINN method sets an upper bound on adaptive weights, preventing excessive suppression of residual term weights and avoiding ill-conditioned optimization problems. This approach ensures convergence and adherence to constraints, improving both boundary condition and residual term accuracy. The I-PINN framework effectively addresses the issues of substantial fluctuations in solution outcomes observed in I-PINN, significantly enhancing robustness across diverse network structures and improving the model's generalization capabilities. The I-PINN method has demonstrated the potential to reduce errors by at least an order of magnitude and improve the convergence rate, all while maintaining computational complexity comparable to the baseline model. The paper's principal contributions include the enhancement of the uncertainty weighting method, the development of I-PINN, and the integration of I-PINN and I-PINN to form I-PINN. The vanilla PINN framework is introduced as a method to solve PDEs using deep neural networks. The prediction function is derived by optimizing the loss function through various optimization algorithms. The loss function comprises a supervised term and a residual term, which measure the degree of approximation to the deterministic conditions and the governing equation, respectively. The PINN method is applicable to various types of PDEs. The paper is structured to provide a comprehensive evaluation of the proposed models through benchmark cases, assessing their performance. The final section concludes with insights on limitations and future directions. The associated code and data are made accessible in the public domain to foster openness and reproducibility. This paper discusses the physics-informed neural network (PINN) methodology for solving partial differential equations (PDEs) and its recent improvements. A generalized nonlinear PDE is considered, which includes various types of equations such as fluid dynamics, heat conduction, and electromagnetic equations. The loss function in PINN is designed to contain deviations from initial, boundary conditions and the PDE itself, with weighted multipliers used to balance these components. The paper also discusses an improved multi-layer perceptron inspired by the attention mechanism in Transformer. This enhanced network addresses the gradient vanishing explosion problem encountered by the original multi-layer perceptron when dealing with complex problems. The improved network embeds the input variable into the hidden state of the network using two different encoders, U and V, and each forward propagation becomes a point-by-point multiplication of the encoder with the conventional MLP. Furthermore, the paper introduces adaptive loss weight functions based on weight upper bounds. In the training of vanilla PINN, it is recognized that while it effectively solves many simple problems, it often struggles with more complex ones. This is due to the lack of a systematic approach for selecting the weights of different loss terms. The proposed adaptive weight functions are designed to dynamically adjust the weights based on the observed upper bounds of the loss terms during training, thereby improving the performance of PINN on complex problems. In summary, this paper presents recent advancements in the PINN methodology, including an improved multi-layer perceptron and adaptive loss weight functions. These enhancements aim to address the limitations of the original PINN and improve its performance on solving complex PDEs. The authors address the limitation of fixed weighting in physics-informed neural networks, PINNs, by adopting a multitask learning approach that utilizes homoscedastic uncertainty to adaptively weight different loss components. This approach enables balancing the convergence and accuracy of PINNs. The method establishes a Gaussian probabilistic model with output U, defining a Gaussian likelihood with mean given by the PINN's approximation and uncertainty parameter sigma m. The joint probability distribution over all tasks is maximized, and the negative logarithm of the likelihood function is taken to obtain the desired loss function. The resulting loss function consists of two terms: a weighted loss function for each task and a regularization term to penalize tasks with high uncertainty. Minimizing this loss function enables adaptive assignment of weighting coefficients to each portion of the losses, balancing their various components. The uncertainty parameter sigma m represents the uncertainty of each task, with easier tasks assigned higher weights and more uncertain tasks assigned lower weights. However, the authors note that the initial loss function may lead to a scenario where one loss consistently dominates during model training, restraining the growth of weights associated with residual terms and inadequate training of the unsupervised learning component. To address this, they propose an adaptive loss weight function incorporating upper bounds, inspired by previous work. The modified loss function introduces a weight upper bound gamma, preventing the weight term from diminishing to zero. This approach serves two purposes. It prevents the weight term from vanishing and ensures that difficult tasks are not ignored during training. The final loss function consists of three components: the weighted loss terms for each task, the regularization term, and the log likelihood term. This adaptive weighting approach enables PINNs to learn from multiple tasks with varying uncertainties, improving the overall performance and accuracy of the model. The proposed IAW-PINN approach introduces a weight-based upper bound to constrain the magnitude of the weights, preventing any single loss term from dominating the training process. This allows for optimal training of both the initial, boundary loss term and the residual term, enhancing overall model performance. The final loss function is given by equation 18, where sigma represents trainable parameters that can be optimized using gradient-based optimizers such as ATOM or LBFGS. Notably, lambda is defined as 1, sigma caret 2 plus gamma 1, differing from the standard PINNs model. To demonstrate the effectiveness of IAW-PINN, a comparative test is conducted between the AW-PINN method and IAW-PINN using the Helmholtz equation. Figures 13 present the results, showcasing the relative errors in solving U and F using different network structures between the two methods. The IAW-PINN approach with an upper bound gamma equals 10 to the power of 3 outperforms the vanilla adaptive loss weighting method in terms of both the solution U and the residual term F. This is evident in the reduced overall error of the model, allowing it to effectively address both supervised and unsupervised learning aspects. The results indicate that the weight-based upper bound IAW-PINN approach effectively reduces the relative errors in solving U and F, demonstrating superior model-solving performance. The comparison of relative errors in Figures 13 highlights the advantages of the IAW-PINN approach over the AW-PINN method. Specifically, the IAW-PINN approach achieves lower relative errors in solving U and F, showcasing its ability to effectively balance the supervised and unsupervised learning aspects. The proposed approach provides a promising solution for addressing the challenges of physics-informed neural networks. The network structure is varied across different configurations, including 3x50, 3x70, 5x50, 5x70, 7x50, and 7x70. The results demonstrate the robustness of the IAW-PINN approach across different network structures, highlighting its potential for applications in physics-informed neural networks. The IAW-PINN method effectively manages the weights of the boundary term and the residual term in the loss function, as demonstrated in Figure 5. This is in contrast to the AW-PINN method, which introduces a significant disparity in the magnitudes of these two weights, leading to optimization challenges and potentially impacting the final solution quality. Figure 4. The proposed IAW-PINN mitigates these issues by adaptively adjusting the weights of the loss terms based on their relative importance. To further enhance the performance of PINN methods in scientific computing, a novel framework is proposed by integrating IA-PINN and IAW-PINN. This integrated approach, referred to as the Improved Physical Information Neural Network, I-PINN, addresses challenges such as vanishing, exploding gradients during PINN backpropagation in complex problems and mitigates the issue of imbalanced training due to scale differences in multi-objective losses. The I-PINN framework incorporates an improved network structure with adaptive loss weighting methods, as illustrated in Figure 6. The pseudocode for the I-PINN algorithm is provided in Algorithm 1. The algorithm initializes the adaptive weight parameters and learning rate, then iteratively updates the model parameters and adaptive weights using the ATOM optimizer. Once the model converges or reaches a specified error threshold, the algorithm terminates and returns the optimized model parameters and adaptive weights. Overall, the IAWPINN and I-PINN methods offer promising solutions for improving the accuracy and efficiency of PINN-based simulations in various fields of science and engineering. By adaptively adjusting the weights of different loss terms and integrating improved network structures, these methods can effectively manage the complexities inherent in multi-objective optimization problems and provide more accurate predictions of physical phenomena. The study presents a systematic comparison of physics-informed neural networks, PINNs, and their variants, including improved PINN, I-PINN, improved adaptive weighting PINN, IAWPINN, and improved adaptive PINN, IAPINN. The Helmholtz equation, a partial differential equation in 2 dimensions, is used as a test case to evaluate the effectiveness of these frameworks. The equation is expressed as squared u, partial differential x squared plus squared u, partial differential y squared plus k squared uq, x, y, equals 0, where q, x, y, is the forcing term that derives the analytic solution u, x, y, equals sin, a pi x, sin, a pi y. The boundary conditions are defined as u, 1, y, equals u, 1, y, equals u, x, 1, equals u, x, 1, equals 0. The improved PINN framework, I-PINN, is employed to compare against vanilla PINN, IAWPINN, and IAPINN. Adaptive weights are initialized to 1, and training data consists of 512 boundary points and 128 interior points, processed over 40,000 iterations using small batches. The network architecture includes 7 times 50 hidden layers, and optimization is performed using the atom optimizer with a maximum weight constraint of 100. The results show that I-PINN outperforms PINN, IAPINN, and IAWPINN in terms of relative errors, with values of 2.68 times 10 to the 1, 2.22 times 10 to the 2, 1.21 times 10 to the 2, and 5.26 times 10 to the 3, respectively. Comparative experiments were performed using various network architectures, and the results are presented in Table 1. The table shows that I-PINN exhibits superior performance across different network structures, with its accuracy improving by an order of magnitude compared to IAWPINN and IAPINN. Figure 7 presents comparative results across different models, depicting exact solutions, predicted solutions, and absolute errors. Figure 8 shows that I-PINN exhibits superior performance compared to PINN, IAPINN, and IAWPINN across various network structures. The results indicate that IAWPINN is less effective in solving problems with relatively simple network structures, sometimes performing even worse than PINN. The figures presented in Figure 7 demonstrate the performance of 4 different models: PINN, IAPINN, IAWPINN, and I-PINN in solving the Helmholtz equation. The top row shows the exact solution, the middle row presents the predicted solution, and the bottom row displays the absolute error for each model. The corresponding relative errors are 2.68 times 10 to the 1, 2.22 times 10 to the 2, 1.21 times 10 to the 2, and 5.26 times 10 to the 3, respectively. These results indicate that I-PINN achieves the lowest relative error, demonstrating its robustness and accuracy in solving the Helmholtz equation. Table 2 presents the relative errors of the 4 models at various k values after 40,000 optimizations using the atom optimizer. The results show that I-PINN consistently outperforms the other models across all scenarios, with relative errors ranging from 3.04 times 10 to the 2 to 4.28 times 10 to the 3. This suggests that I-PINN is a reliable and efficient method for solving the Helmholtz equation. Figure 8 compares the relative errors of the 4 models across different network structures. The results show that I-PINN achieves the lowest relative error in all cases, with errors ranging from 1.01 to 1.02. This demonstrates the robustness of I-PINN to different network structures and its ability to generalize well to different scenarios. The Klein-Gordon equation, a fundamental equation in relativistic quantum mechanics and quantum field theory, is a nonlinear partial differential equation of significant importance in scientific disciplines such as quantum mechanics, particle physics, and nonlinear optics. The equation is formulated as a nonlinear partial differential equation, and its solution is crucial in understanding various physical phenomena. The performance of I-PINN in solving the Klein-Gordon equation is not presented in these pages, but its robustness and accuracy in solving the Helmholtz equation suggest that it may be a promising approach for solving this equation as well. Here is a combined summary of pages 19 and 20 of the research paper. The authors formulate a nonlinear Klein-Gordon equation, which is a partial differential equation that describes the dynamics of a scalar field in a spacetime continuum. The equation is defined as U plus alpha increment U plus beta U plus gamma UK equals F, X, T, with initial and boundary conditions specified. The goal is to solve this equation using physics-informed neural networks, PINNs, and variants. The authors employ a network architecture with 7 hidden layers of size 50 and utilize the atom optimizer to train the PINN, IA-PINN, IA-WPINN, and I-PINN models over 40,000 iterations. The resulting relative errors are compared, and it is shown that I-PINN demonstrates superior solution accuracy, achieving at least an order of magnitude improvement in relative error compared to the other 3 methods. The authors also investigate the impact of different adaptive weight caps on the performance of I-PINN. Various adaptive weight caps are set, and the effects on the solution results of I-PINN are analyzed. The results show that as the weight cap increases, the relative error gradually decreases and tends to level off. Figure 9 presents the exact solution, predicted solution, and absolute error heat map for I-PINN, as well as comparisons with PINN, IA-PINN, and IA-WPINN. The figure depicts the superior performance of I-PINN in solving the Klein-Gordon equation. The authors' results demonstrate the effectiveness of I-PINN in solving nonlinear partial differential equations, highlighting its potential for applications in physics and engineering. The paper discusses the application of physics-informed neural networks, PINNs, to solve partial differential equations, PDEs, and their variants. It presents a comparative study on the performance of PINN, IA-PINN, IA-WPINN, and I-PINN models for solving the Klein-Gordon equation with different network structures. The results show that I-PINN outperforms other models in terms of relative error, especially when using a 7 × 50 hidden layer structure with 40,000 iterations of atoms optimizer. A detailed analysis of the relative error comparison across various network structures and models is provided in Table 3. This table demonstrates that the I-PINN model consistently achieves lower relative errors than the other models, regardless of the network structure used. Furthermore, the paper applies the proposed method to study the problem of lid-driven cavity flow, which is a benchmark problem in computational fluid dynamics. The incompressible Navier-Stokes equations are used to analyze this example, and the results provide insights into the fluid motion within the cavity, including the distribution of velocity and pressure fields. In conclusion, this study showcases the effectiveness of I-PINN in solving PDEs and its variants, highlighting its potential for a wide range of applications in engineering and science. The paper discusses the development and evaluation of a novel approach called I-PINN, which aims to enhance both the predictive accuracy and convergence of solutions for partial differential equations, PDEs. The I-PINN model is compared with PINN, IA-PINN, and IA-WPINN in terms of performance. Figure 12 illustrates the comparison of loss histories for I-PINN using a 7 × 50 hidden layer structure with 40,000 iterations of atoms optimizer under different adaptive weight upper bounds. The results indicate that the I-PINN model outperforms the other models in terms of relative error, achieving a value of 5.12 × 10⁻². In the context of learning velocity components and potential pressure fields, the I-PINN model was trained using the atom optimizer for 40,000 iterations. The configuration of boundary and residual points was consistent with a previous section. Figure 13 summarizes the experimental results, comparing reference solutions and predicted solutions obtained from different models. The velocity fields obtained by I-PINN were very close to the reference solution, with a relative error of 5.12 × 10⁻². The paper concludes that the I-PINN model has demonstrated superior performance, exceeding the accuracy of PINN, IA-PINN, and IA-WPINN by at least an order of magnitude, all while maintaining computational efficiency. This novel approach can potentially revolutionize the field of PDEs by providing more accurate and efficient solutions. This study presents the key findings of I-PINN, a physics-informed neural network (PINN) framework that exhibits robust performance across various network structures and problem complexities, demonstrating strong generalization capabilities. I-PINN integrates an enhanced architecture with improved adaptive weighting, resulting in stable and convergent optimization for partial differential equations, PDEs. The innovative framework provides a robust and accurate solution strategy for PDEs, but further research is necessary to explore its potential applications across diverse disciplines. Open questions include the selection of upper bounds for the weights in IA-WPINN, which remains an empirical choice and may vary for different problems. Future work will involve examining the combination of min-max optimization and an improved architecture as an alternative to weight upper bounds in PINNs. Additionally, the exploration of adaptive weighting strategies to balance loss components in PINNs is necessary, as well as investigating the scalability of I-PINN to higher dimensional PDEs and more complex physical systems. The I-PINN framework will be extended to handle multi-scale and multi-physics problems, enhancing its applicability in real-world engineering and scientific challenges. The utilization of I-PINN in the context of inverse problems also requires exploration, aiming to broaden its functionality across various problem-solving domains. This research is supported by the National Natural Science Foundation of China, the Scientific Research Foundation of Chengdu University of Information Technology, the Key Laboratory of Numerical Simulation of Sichuan Provincial Universities, and the Science and Technology Department of Sichuan Province. The authors declare no potential conflict of interest. References are provided to relevant studies on residual-based attention in physics-informed neural networks, physics and equality-constrained artificial neural networks, multitask learning using uncertainty to weigh losses, and other applications of PINNs in solving PDEs. The literature review highlights recent advancements in physics-informed neural networks, PINNs, and their applications in solving forward and inverse problems involving nonlinear partial differential equations. Jagtap et al. 1012 introduced adaptive activation functions to accelerate convergence in deep and physics-informed neural networks, while Kendall et al. 14 proposed a multitask learning framework using uncertainty to weigh losses for scene geometry and semantics. Karniadakis et al. 13 provided a comprehensive review of physics-informed machine learning, emphasizing the importance of incorporating physical laws into neural networks. Liu and Wang, 16, developed a dual-dimer method for training physics-constrained neural networks with minimax architecture. Liu et al. 17 introduced DeepXDE, a deep learning library for solving differential equations. The review also covers various techniques for improving the performance of PINNs, including self-adaptive physics-informed neural networks, 19, optimally weighted loss functions, 21, and understanding and mitigating gradient flow pathologies, 22. Wang et al. 23 analyzed the failure of PINNs to train from a neural tangent kernel perspective. Recent studies have also explored the application of PINNs to multiscale problems, 24, and the development of self-adaptive loss-balanced physics-informed neural networks, 27. Zhang et al. 28 proposed physics-informed parallel neural networks with self-adaptive loss weighting for the identification of continuous structural systems. The references cited in the literature review demonstrate the growing interest in developing and applying PINNs to various fields, including physics, engineering, and computer science. The studies highlight the importance of incorporating physical laws into neural networks and the need for further research in developing efficient and robust PINN architectures. The equations and algorithms presented in the references aim to improve the performance and accuracy of PINNs, including adaptive activation functions, dual-dimer methods, and optimally weighted loss functions. The figures and tables in the references provide visualizations of the results, demonstrating the effectiveness of the proposed methods in solving various problems. The literature review provides a comprehensive overview of the current state of research in PINNs, highlighting the key challenges and opportunities in this field. The references cited demonstrate the potential of PINNs in solving complex problems and the need for further research in developing efficient and robust PIN architectures.